In this lecture, we will discuss very similar concepts to last time, total change versus rate of change, but in other contexts other than the distance, velocity, and acceleration. So here's our first example. An IV delivers infusion at the rate that is described by the following function, cubic centimeters per hour, where time is measured in hours. This infusion contains drug concentration that is known to be 0.1 milligrams per cubic centimeter, whereas to find total amount of fluid and total amount of drug delivered to the patient over the first hour. This is actually a very realistic application because the IV machines will indeed tell you the rate of change of an infusion and not the amount of infusion itself. So you're going to have to figure out by which point in time did the patients get enough fluid into their system. So what we have here is the rate of change, and we need to find the total amount of fluid, which means that we're once again drawing the connection between the derivative and the function itself. So the total amount of fluid is going to be the integral, the sum of the rate at which the fluid was injected over the amount of time when it was injected at. So 100, 1 minus t cubed with respect to time over the first hour. So from 0 to 1. Okay, so let's pause here for a second again. This is the rate of change of infusion. So you can think of that as the rate at which the fluid was supplied, which means the derivative of the amount of fluid. Recall that by the fundamental theorem of calculus, the derivative and the integral's actions get cancelled, which means that now I will simply get the fluid calculated at the end of the process minus what the patient had started with. So this is exactly what I want. The total amount is always the integral of the rate of change of said amount. Now, once I have that, the rest of it is simple calculations of antiderivatives. So I'm going to have 100t minus 100t to the fourth over 4 computed between 0 and 1, and this will come out to be 75. My rate was in cubic centimeters per hour, but I've multiplied by the number of hours throughout the process, so this will be in cubic centimeters. Now, this is the amount of fluid as instructed to calculate through the rate of change of fluid. The amount of drug depends on the concentration of the drug in the fluid that the patient is receiving. So the second part is similar kind of like to the gasoline question at the end of last class. The total drug amount will equal to the total fluid amount, which is 75 cubic centimeters, times the concentration of the drug in that fluid. So 0.1 milligrams per centimeter cubed, which altogether will come out to be 7.5 milligrams. This problem is a great standard example of problems of this type. Given the rate, figure out that you're going to have to calculate the antiderivative of it to get to the total amount. Let's see another example in a different setup. So here we have trees and the way that trees grow. A trunk of a tree, we're assuming, has the shape of a cylinder. That's not a far-fetched assumption. Most trees do, in fact, look something like this, with branches and whatnot. And we're going to assume that it grows incrementally widthwise. So it's acquiring the rings as the time goes on. Note that the formula we're given is the growth rate of a tree's trunk radius. So the growth rate, not the radius itself. R stands for rate, not radius. And this is in millimeters per year. Now, it does follow the sinusoidal curve, which also makes sense because it would make sense that trees grow slower in the winter and faster in the summer when they have more nutrition available. We're given that the initial radius is 1 millimeter and are asked to find the actual radius of the tree at time t. So similarly to the last problem, we are given the rate, we're asked to find the total of the dimension. Therefore, we know that these two are going to be connected by an integral or an antiderivative. The total growth from time 0 to time t is then given by the integral between 0 and t of my growth rate. I'm actually going to first of all write it using words, so we once again notice the actual connection. The total is given as the integral of the rate. Okay, so again, the derivative and the integral are inverse processes, which means that what I get all together is the growth that happened between t and 0. Now, their next step is the simple anti-differentiation. So here, I'm going to take the antiderivative of 1.5 minus sine t, and for that, I need to remember some antiderivatives of these functions. So I'm going to have 1.5t. The antiderivative of sine is negative cosine, so I'm going to get negative of a negative cosine, and therefore plus cosine of t to be computed between 0 and t. So what am I going to get all together? If I compute this number, I am going to get 1.5t plus cosine of t minus 1. So notice when I plug in 0 into here, I'm going to get a 0, whereas cosine of 0 is actually negative 1. Now, what I am told, though, is that we begin with radius of 1 millimeter, which means that while this is giving me the total growth that happened from 0 to t, I need to add the initial radius to this total growth in order to obtain the actual radius at time t. So radius at time t will be initial radius, which is 1 millimeter, plus growth that actually occurred. So that is 1 plus whatever I ended up getting from the integral, which is this 1.5t plus cosine of t minus 1. Now, of course, I notice that my 1 and minus 1 cancel, so overall I get 1.5t plus cosine of t. And this altogether is my radius at time t. Take a look at this example and try to think of another way to actually approach it, because there is a slightly different variation on the actual process to implement this initial radius and account for it in the integration process itself. What we can look for here too, though, is we actually know the functions. So the function for the growth rate is given by this, and the function then for the radius is given by this. Let's graph them and see if this is something that we can recognize. So here I have, let's start with this one. I have my function on the left here, you can see, is the 1.5 plus sine of t. It should be minus, as in my problem. Whoops, minus. There we go. And what I have is the sinusoidal curve that we decided was a reasonable thing because the trees might in fact pick up growth rate and then lower it as dependent on the nutrients they receive. Now, as the time goes on, the radius keeps growing, and therefore the total radius continues to increase. This can be seen here because the area under the curve as time goes on continues to increase. Sometimes it increases slower, sometimes it increases faster, but it nonetheless increases all throughout. So on the other hand, we can take a look at the formula that we derived that corresponds to the total radius. And this is an increasing function all throughout. Whether the rate slows down or picks up, it does continue to increase in this case. So my blue function that corresponds to the radius continues to increase. You can notice that when the rate of increase was the lowest, this also corresponds to when the tangent line to this graph would be less steep, whereas when the rate was high for my rate function, that is also, of course, when the total radius will have a very steep slope value, because that is the connection between the antiderivative and the function itself. In our next application, we'll take a look at hormone levels and circadian rhythms. Now, circadian rhythms are 24-hour cycles that are basically part of the body's internal clock. The most famous, I suppose, one is the sleep-wake cycle. So something that happens on the 24-hour period where one of the hormones in your body gets produced during the night and the other one, on the opposite, gets reduced during the night but produced a lot more during the day. This is going to be the case for any kind of hormone level, there are basically two separate processes. The first one is the secretion rate of cells that produce the hormone or the hormone production. And the second one is the deactivation by some enzymes secreted by other cells or the removal of the hormone. The cyclic patterns are exactly what's called circadian rhythm, and we can analyze these from the point of view of the rates of the production of whatever hormone we are interested in. So let's take a look at a general setup here. We have two functions representing the production, that's the one labeled P, and the removal of the hormone over a certain period of 24 hours, starting at midnight here. And we have a few questions that we can ask about these graphs. So for example, when is production rate maximum? Now remember that these graphs are the graphs of rates. So if the question asks about the maximal rate, all we have to look at is where is the highest point on the production rate graph. And that happens to be somewhere around here, so approximately at 9 a.m. For the second question, when is the removal rate minimal? And if we take a look, that's the lowest point on the removal rate graph, and that looks like it's approximately around noon. So if the question asks about the rate and the graph is that of a rate, reading off the graph is very straightforward. On the other hand, what if we ask about the hormone level? So again, recall that the graph represents rates. The hormone level, therefore, must be something that we calculate slightly differently. When is the hormone level the highest and when is it the lowest? Let's think about how the amount of hormone changes in the body over time. So we're going to think about the net change of hormone level over, let's say, a 24-hour period. We've already discussed that it's governed by two processes, the production and the removal. The total is going to be the total amount produced minus the total amount removed. Now, this is again when we get to draw the connections between the rate function and the total amount function. Remember that in order to go from the rate of production to the total amount produced, we're going to need to take an integral. So this is going to be an integral over some time interval, let's call it between A and B, of the production rate minus integral over the same time period of the removal rate. Now, if we're going to consider both of these integrals over the same time period, then we can combine the two of them together. And what are we going to get? We're going to get that we have an integral from A to B of the production rate minus removal rate, all with respect to time. Let's take a look at this formula with keeping in mind what we've discussed earlier. If we have an integral where you're taking a value and subtracting something from it, that can be interpreted on the graph as the area between the two graphs. This is exactly how we set up this area formula, area between graphs. Now that means that we can interpret our question as a question about area. When is the hormone level the highest is when the area between the two graphs is the largest. So as the production rate increases and then decreases, at the same time the removal rate decreases and then increases, at which point is the area between the two graphs the biggest? Well, I can see that if I move along the time axis, let's say if I stop somewhere here, the area between the two graphs will be something like this. It continues to increase up until this point, and then it becomes negative because now the removal rate actually surpasses the production rate. So the area bounded by the two graphs is the highest around 3 p.m. So the highest around 3 p.m. What about the lowest? So now I'm interested in when is the area covered altogether was the lowest, let's say starting from 0 all the way down. Well, if I start from 0, the first thing that happens is the area covered here, except for, see, the top graph here is the removal graph, and the bottom graph here is the production graph, which means that this area will actually be negative. After this point, the area acquired will be positive and therefore will start increasing. So the area is the lowest at exactly this point, because up until now, it's going to count negatively. So the level of the hormone in the blood is the lowest around 3 a.m. Now, let's also write down what we've actually noted. If the production is bigger than the removal, so what we have here is the production is bigger than the removal, so I am subtracting a smaller number from the bigger one, which means that integral will be positive. So integral here is positive, and that is because, again, this will result in the actual accumulation of the hormone in the system because it gets produced faster than it gets removed. On the flip side, if the production is less than the removal, then what would make sense is that the total amount of hormone is actually decreasing because it gets removed at a faster rate than it gets produced. Now, in terms of the integral here, if production is smaller than removal, that means that we're subtracting something bigger than what we're subtracting from, and in this case, then the integral is going to be negative. Now, this is always nice in order to confirm your logic, to actually think back to the setup and see whether the positive and the negatives in the integral correspond to what we expect in the application itself. Let's take a look at another similar application, that of a level of glucose. Now here we have the level of glucose depends on the intake from food and clearance due to glucose metabolism in the liver, for example. Here are the two general graphs. One is the intake and one is the clearance. We would like to simply express the total glucose level as a definite integral and then figure out at which point during this 5-minute interval was it maximal. So similar to the previous problem, the total glucose level will be the difference between the production and the clearance. So in this case, the difference between the intake and the clearance of the glucose from the blood. And this will be taken between some 2 points in time, A and B. Now again, to figure out when this is maximal, it's best to think about how this is interpreted in terms of area on our graph. Mostly because we don't have these as actual functions. The only thing we can work with is the graph itself. So all we need to do is think about what this is on the graph. And on the graph, once again, this is the area between the two functions. So the question is simply asking, when is the area bounded between the two functions is the greatest? Keeping in mind that there's a minus here, so when the first function is above is when you will get positive total contribution, and when the second function is above, you're gonna get negative total contribution. So going from 0 towards 5, we're thinking of what happens to the area between the graphs. Well, here it continues to grow because the contribution toward it continued to be positive. But then after this point, the second graph is now on top, which means that area that is counted here will be counted negatively. So the maximal amount occurs at around, let's say, 2.3 minutes. About 2.3 minutes. Okay, so once again, this area will be positive, this area will be negative, so the maximal will occur at the point at which we've managed to accumulate the most positive area and none of the negative one. Now, another concept we're going to introduce in this chapter is the concept of an average value of the function over a specific interval. So this is the expression that defines the average value of the function. Let's unpack this, and let's unpack it in terms of the graph. So if I sketch my function f of x, I am interested on I'm interested in this function on some interval from a to b. And now let's take a look at what the average value expression is giving me. I have, first of all, this number b minus a. Now b minus a will give me the distance in between. So this b minus a actually corresponds to the length of the interval at which I'm considering my function. What about the integral itself? According to our definition of a definite integral from the graph, the integral is the area between the curve and the x-axis between the values of a and b. So this is the area under the curve, under the graph, let's say. Right? So let's think about what that actually means as we're performing these calculations. This is my area under the curve. I take this total area and then divide, because this is 1 over, I take the total area and divide by the length of the interval. So this area in itself is non-standard shape, but I divide by a very straight linear dimension. So altogether, what this gives me is the height of a rectangle that will produce the exact same area on this interval. Let me write this down. Take a second to really read it over and think it through, and then we're going to take a look at the graph again. This is the height of rectangle that covers the same area as my integral on the interval from a to b. Okay, I'm dividing by the length of the interval, and therefore I'm getting the height. You can think of this formula sort of having solved this for the integral. Length times height will produce the area under the graph. The area under the graph itself is not a rectangle, but what the average gives me is this flat rate, basically, where the area under this flat rate will be exactly the same as the area that the integral computed to fit under this non-flat curve. Okay, so in this case, I can guesstimate that it's going to be approximately here. This is going to be approximately my average. Let me, in fact, draw it in. Something like this. And that is because I can see that whatever area counts extra here did not get counted here. So I am fairly certain that this estimation is not too far off. This rectangle will cover the exact same area as I have shaded in red. So the same area as between the curve and the x-axis, the same area as the integral will cover, but now in a rectangle shape. And once again, this is where the terminology flat rate, for example, comes from, or like a flat average. This is the number that will produce the same area, but it's a flat number, not a curvy graph. Now, with this in mind, we can, of course, compute average values of any given function over any given interval by simply utilizing the formula. So let's plug it in. What we have here is the average, which is denoted f bar, is equal to, and let's see how we can actually use the formula. The interval itself is what is labeled a and b in this case, and therefore I will have 1 over 4 minus 2. This is my value for a, this is my value for b. Next comes the integral from 2 to 4 of my actual function. The computations themselves are going to be fairly straightforward. So what I have is 1/2 in the front, then antiderivative of x squared, which is x cubed over 3, and I have to compute that between 2 and 4. If I plug it in and actually calculate it, it's going to come out to be 28/3 or approximately 9.3. Let's sketch a rough graph and see if that number even remotely makes sense. So I will need to sketch my parabola. and think about the area between 2 and 4. So my parabola y equals x squared, something like this. I am interested between 2 and 4. Now at 2, this here, because the function is y equals x squared, is going to be 4. And then at 4, because my function is x squared, let me actually note here, is going to be 16. So again, what the average is computing is I need to find the height of a rectangle that spans the interval from 2 to 4 that will give me the same area coverage as what I have shaded in red here. Now, let's actually sketch 9.3 here. So eyeballing it, it's going to be probably around here. And so what that means is if I now draw a straight line between 2 and 4, the rectangle under that straight line that spans this entire interval from 2 to 4, this blue rectangle will cover the exact same area as the red shaded, non-standard, non-regular looking area. And this looks pretty reasonable, right? I can see that the area I'm accounting for here in the rectangle is approximately equal to the area I'm not accounting in the rectangle, but I'm accounting in under the curve calculations. So this actually seems fairly realistic that even on my rough sketch, this rectangle will cover the same area as this red shaded one. Now, this can be used to calculate a variety of averages that we actually care about. So for example, let's consider the formula for the day length. This is the formula, it involves the sine, and that's not surprising. We notice that throughout the year, the day length increases during the summer and then decreases during the winter. Here, t equals 0 corresponds to the spring equinox when night and day are actually the same length at 12 hours. And then we can use this formula to compute the number of daylight hours on day t after the spring equinox. The first question is, what is the smallest value of f of t? Now, there's a number of ways to analyze it. The second question actually asks for the largest, so we might want to think in terms of how can we kill two birds with one stone here and analyze the function more generally than just finding the smallest first and then doing a completely brand new process to find the largest. The nice thing about trigonometric functions is that we know that they're bounded. Sine of anything is always bounded between -1 and 1. So no matter what goes inside the sine, and let me generally call it theta, the value of the sine, the biggest it can be is 1, and the smallest it can be is -1. So what does that mean for our function? This guy here, the biggest it can be is 1, which means that the biggest my function can be is 12 plus 4 times 1, which is 16. So this implies that my f of t, the largest it can be, is 16. What about the smallest? Well, the smallest sine can be is -1. So what happens if this entire expression is equal to -1? Then I'm going to get 12 plus 4 times -1, so 12 minus 4, or 8. So right away, just thinking about the largest and the smallest value of a trigonometric function gives me the largest and the smallest value of this transformation of the trigonometric function. The next question asks, find the average day length over the year and confirm it on the graph. So first of all, let's utilize the formula. The formula says that the average is equal to 1 over the length of the interval, and here I'm taking it over the year, so 365 days, of the integral of the value that I'm interested in. So 12 plus 4 sine of 2 pi t over 365 with respect to time, all taken over the year, so between 0 and 365. Now, these computations are not terribly insightful, and it's just you're going to have to play a little bit with making sure that you take the antiderivative of this sine with this big argument in it correctly. But the computations in the end give the value of 12 hours. So what that means is that the average day length over the course of the year is actually 12 hours. Does that make sense? Well, sine is a fairly periodic function. The smallest value is 8, the largest value is 16. So as it oscillates between the two, it makes sense that the average is right in the middle, which is of course 12. How can we check that on the graph? Well, here is the graph of that function. You can see it on the left here. And what I am doing is just drawing the area under the curve, which is what the integral in my average value of a function setup will give me. Now, recall what we talked about, that overall, the average gives you the height of a rectangle that will cover the exact same area as the integral covers in this graph. So what I'm going to do is I am basically going to think about 0 to 365, and I'm going to raise a rectangle height. So for example, if I stop here, has my rectangle yet covered enough area to equal to the red shaded area? Well, no, not yet. What about if I move my rectangle way up there? Clearly now my rectangle under this flat horizontal line covers more area than the red shaded. So I have to be somewhere in the middle. Now this seems still too much because the white area on the right covers too much of the area not included, but this seems to be just right. Make sure that you really see what the graph is telling you here. Let me rephrase this again. The area of a rectangle that I now am forming with this horizontal line over the region from 0 to 365, the area of this rectangle is equal to the red shaded area that corresponds to the area under the graph of my daylight function. And that means that that is exactly the average. Now, for another example of the average, let's take a look at the various calculations for the amount of rainfall here. What we have is the rainfall pattern of constant 20 millimeters over the first day, a steady increase from 20 to 50 over the next day, then 50 millimeters, a drop from 50 to 40, and then a flat 30. So you're going to have to construct a piecewise function that replicates exactly that. As we go from day 1, 2, 3, 4, and on to day 5, what we're seeing are the patterns that we would like to actually note. So let's say I introduce a scale. Every 20 seems to be like the scale that would actually work out here. And let me just start sketching what we're seeing. A constant 20 millimeters on the first day. Constant means that for the first entire day, the rainfall stays at 20. So this is time of day, and this is, let's call it the amount of rain. Then over the next day, we have a steady increase from 20 to 50. So over the next day, a steady increase will take me to 50, which is up here. So something like this. I'm going to leave the rest of the graph for you to actually fill out, just to make sure you can practice reading the information given and plotting it on the graph. The first question asks, what is the total amount of rain that actually fell during this period? So notice that what we're seeing here are the rates, millimeters on the first day. So 20 millimeters per day means that in the entirety during the first day, we have acquired 20 millimeters of rain. On the second day, it went from 20 to 50 throughout the day, which means that the total is the area under this graph here. This is how you will compute the first part, area under the graph. And then the second part asks, once you have the area under the graph, calculate the average. Now, if you have the area under the graph and you're calculating over the period of 5 days, all we have to do is take the total and divide by 5. So this will be area under graph divided by 5 days. This will, of course, produce some kind of an actual number. And what I would ask you to do, as I'm leaving this exercise for you to complete, is once you have this number, interpret this back onto the graph. What does this number represent on the graph? If the number comes out being, for example, 30, for the sake of an argument, I don't think it actually is 30, but if it is 30, that means that the average daily rainfall was 30, which means that the area covered under 30 for 5 days would have been the same as the area that you've computed in the first part. Once you get your number, plot that on the graph and write a sentence about what that average represents on the graph. For the last example here, let's think about power functions in general and how does the power affect the actual average. So here we're asked to compute the average for the general x to power n function, so over the interval from 0 to 1. So the formula tells us it's 1 over the length of the interval, which is just 1, and then I'm going to have to take the integral over my interval from 0 to 1 of my function, which in this case is the power function. Now, the general antiderivative of this is x to power n plus 1 over n plus 1. I'm assuming that this n is actually greater than 1, so I'm not going to get into any kind of reciprocal functions. These are actually power functions. So starting, I guess I can actually assume greater or equal than 1. Starting with the line, going for parabola, and then the cubic function, and so on. Now I'm going to have to actually compute this between 0 and 1 because what I was given is a definite integral. So now I plug 1 in for x. What am I going to get? 1 to power n plus 1 over n plus 1 minus, and then I'm going to plug in 0 in for x. This is when it's important to remember what the actual variable is and what the constants are. Now 1 to power anything is just 1, so this is going to be 1 divided by n plus 1. And 0 to power anything is just 0, so this whole term is going to be 0. So my average is 1 over n plus 1. Part 2 is asking what happens as n becomes arbitrarily large. So let's compute our average as n goes to infinity. So as per the calculations in part 1, what I actually have here is the limit of 1 over n plus 1. Now, of course, if n goes to infinity, the whole denominator here tends to infinity. And so what I get is 1 over infinity, 1 over a very large number, which in the limit goes towards 0. So what this is saying is that for very large power functions, the average over the interval from 0 to 1 is actually tending to 0. Let's see if we can understand this graphically. So what does a power function x to power n look like on the interval from 0 to 1? Now notice that I don't actually have to draw the negatives here. I'm only interested in the positive because my interval is from 0 to 1. So whether the function is an odd power and therefore a cubic, or an even power and therefore a parabola looking shape, doesn't really matter because I'm not interested about what happens on the left-hand side there. What I can draw is just the general shape of a power function starting at 0. And what I'm interested in, of course, is the area covered under the curve here and what height of a rectangle would cover the same area. So what I have drawn here is approximately the average of my sketch, right? Somewhere here will this rectangle cover the same area as the curve covers without it, because I can see that my positive and negative contributions above and below the rectangle would have actually approximately evened out. But the one thing to remember is that the power functions, remember the dominating power analysis, as n goes to infinity. So for example, if this was x squared, x cubed would go under it, and then the domination would start. X to the fourth would be slower growing still near the origin. X to the fifth would be flatter still. The larger the power, the flatter it is near the origin. These graphs get closer and closer to x-axis with increasing power of n, which means that if n tends to infinity, this graph is going to be very, very flat, very close to the axis, and therefore the average will indeed approach 0.